All right, so this video is going to be on the reduction of alkynes, which we kind of saw a little bit about, but there's a couple other reagents that we need to introduce. So on the previous video, we saw that if we took an alkyne and we added H2, let's just say two equivalents or an excess via, and then we also added palladium on carbon, we would get an alkane, right? So we completely reduced that alkyne to an alkane. And also remember that this process was super fast, right? Like this fast elevator running in the pink chucks. Like, whoa. So it completely skipped over the alkene product, right? And so we weren't able to isolate that. And that's a bummer because alkene products are really desirable. So let's introduce a couple ways that we can isolate an alkene. But remember, we have two stereoisomers for alkenes. There's a cis alkene, and then there's also a trans alkene. And you can totally isolate these two isomers. Say what now? Gary Payton say what now? So I don't know if that's crazy to you or not, but that's crazy to me. You can isolate. You can literally do two different processes and get a cis alkene and a trans alkene, like from an alkyne, for real. So one of them, well, we kind of introduced them already, but you don't know which one is which. So the palladium on calcium carbonate with lead acetate and quinoline, that one we introduced. Remember, and I drew the lead acetate like that, but I didn't draw the second one on there, and I just feel like that was silly. I should have drawn both. And just to clarify, I'm drawing that again for you. Okay. This particular set of reagents is called Lindlar's catalyst. Okay, and it's just named after the dude that found it. Okay, so Lindlar's catalyst is all of those reagents, and we'll refer to it as Lindlar's catalyst, and it isolates the cis alkene. Okay, and the reagents that produce the trans alkene are elemental sodium and ammonia NH3, and that's not NaNH2 sodium amide, because that's Na plus and NH2 minus. Do not confuse these because they are very different. Okay, so look for that extra hydrogen. Look for the, like, you just need to not do that. Okay, so I'm pointing it out now for you. Lindlar's catalyst is, as I mentioned before, poisoned. It's just like, so of course we do have to add the H2. I didn't put that over because I'm just introducing the catalyst, but H2 is going to be added to the alkyne with the palladium from the Lindlar's catalyst, and so it's poisoned and it doesn't react after the first reduction. So what you end up getting is the cis alkene, and it's cis because it occurs on the surface of that palladium that is adsorbed to the calcium carbonate. So it's a solid material. This is actually called heterogeneous catalysis, because a heterogeneous mixture is like when you have a solid and a liquid, for example, two different phases. Okay, and moving on to the sodium and ammonia reduction process, this is actually a radical mechanism. Okay, ish. Okay, because it's kind of both. You got your normal anion as well as your radical. But so let's talk about the trans alkene specifically, because the Lindlar's catalyst, we don't need to go over that. It's the same process as far as you're concerned, but it can't react any further, and you just isolate the cis alkene product. Okay, so let's take a look at the alkyne. Remember, this is going to result in the formation of a trans alkene, but how does that happen? So first, what we want to do is add Na, sodium, elemental sodium. And now, what do we know from general chemistry? What do elementals, like metals, like to do? Well, they want to give up an electron, right? So that's what this guy's going to do. Metals, alkali metals and alkaline earth metals are really good at giving up electrons to gain that positive 1 or 2 charge. And so that's what this guy does. He's going to give up one single electron or reduce the alkyne, right? And this is a fishhook arrow. Just want to remind you guys that represents the flow of one electron, okay? And what that does is that kicks this pi bond over to that carbon. And this is a regular arrow, just with it represents 2 electrons flowing, okay? Um, just kind of going back to the basics a little bit, just to keep your mind fresh. But what that results in is the formation of a radical anion as well. So we have a lone pair on the left side that's negatively charged, and we got a unpaired electron on the right side. Okay, and this was all by the reduction using elemental sodium. Now this hydrogen on ammonia comes along, and that hydrogen has a pKa of 38 is what it is. Yeah, I wanted to say 44, but the pKa of the alkene. I'm sorry, I'm kind of comparing it to the alkene because I want to. And that pKa is about 44. Okay, and that is a stronger acid, JK, not a stronger acid. Um, the pKa of 44 is a weaker acid, and therefore a stronger base. That conjugate base would be a stronger base than the NH2 minus. And so that means that this guy can actually deprotonate that ammonia. And that's exactly what happens here. Okay. Um, so after the removal of that proton from the ammonia, you get this intermediate. This is another radical species. It's neutral though at this point, and um, an additional electron is added from another sodium atom. Again, that fish hook adding 1 electron, and so what's that going to result in? Well, it results in an anion, right? A carbanion, and that carbanion again is strong enough to remove an NH proton. Okay, and removal of that proton affords the transalkene. Remember, transalkenes are more stable, and that's why you get that product. Also, you have the R groups as far away from one another as possible, and then throughout the mechanism, you'll notice that the electrons are as far away from one another as possible as well. And so it's different than the surface catalytic reaction with palladium because that happened on a surface rather than in solution, so you can actually approach from both sides when you're in solution, and so you obtain the more stable transalkene. Okay, so let's take a look at what these reagents can do to just one single molecule, for example. So let's say we've got this actually, it's got a lot of functional groups in it. So let's throw some hydrogen and Lindlar's catalyst at it, as well as sodium and ammonia, and see what we get. Well, we've got, since we're focusing on Lindlar's catalyst and ammonia and sodium, we are focusing on this alkyne, right? And so this alkyne for Lindlar's catalyst, remember, is still a surface reaction. So you're going to end up with syn addition or the cis alkene, but it's also poisoned, so it stops reacting, and you end up with the cis jasmone. And then this one right here is the trans product, right? So, and if you don't know, this is I think it's like kind of like a defense mechanism or something, or a stress hormone from jasmine, the plant, and it smells amazing. It's like, love the scent of jasmine. It's one of my favorites, and so this is the compound. Cis jasmine is the normal one. I think that's naturally occurring, but trans, when you make it, it does form, and so you're gonna get some of that too. They smell the same apparently. Let's throw H2 and palladium on carbon though. What do you think we get for that? Pause it if you want to think about it. Check that out. First of all, in a previous video we told you H2 and palladium on carbon can reduce ketones as well as alkenes as well as alkynes completely, and so we end up with this alcohol compound that is completely saturated, all the hydrogens. Okay, so I think that's a cool reaction. It's fun because you're basically just destroying all the functional groups in that particular compound. Whereas if you use if you have use judicious choice in the reduction compound, then you can kind of manipulate it and isolate different compounds. So isolate maybe more desirable ones, like the amazing scent of jasmine. So now let's take a look at reductions using lithium aluminum hydride. So lithium aluminum hydride looks like this. We've got a dipole moment headed towards that hydrogen, just like the BH3 or BH4. And that's because hydrogen is more electronegative than aluminum. And so it's got that negative charge on it, or the delta negative. And it is, in fact, a source of hydride, or H minus. So when we're using it, that's the way we want to think of it. Okay, it's going to be a source of a hydride nucleophile. Okay. Now let's say we have this alkyl halide. Now hydride from aluminum hydride, lithium aluminum hydride is a good nucleophile. So I got a question for you. I got a question, if I may. What do good nucleophiles do with, specifically in this case, primary alkyl halides? So we already know this. So we should know the product of this reaction. They do SN2 reactions. You know what I'm saying? So little SN2 action, backside attack, kick that bad boy out, and then we end up with a fancy alkane. So remember, this is hydride is coming from lithium aluminum hydride, and so that kind of is a fairly large molecule, and the rate of reactivity does decrease as you go from a primary to secondary to like tertiary, for example. So just kind of like that general trend for SN2 in general, right? So you get an alkane from alkyl halides. So all right, so one reagent that I didn't add was because it's kind of silly in my opinion, but it is water. And so water is used to quench that reaction, kind of stop the reaction, kind of react with all of the lithium aluminum hydride that might be present still. But that's something you'll see when you do these problems. So another thing that lithium aluminum hydride reacts with is epoxides. And so again, lithium aluminum hydride is a source of a good nucleophile, a strong nucleophile. What do we know about strong nucleophiles reacting with epoxides? They react at the least substituted carbon. All right? You got it. If you got it, I mean, yay. So what happens is it attacks right there. You get that epoxide popping open. And then you end up with the alk oxide with with the hydrogen on that carbon. I'm not gonna draw that. That's boring. So, but the water actually makes sense here because now we got to protonate that guy and end up with the alcohol product. Okay, and there you have it. So don't forget, lithium aluminum hydride is the source of a great nucleophile. And so it reacts as such. So what's cool about this is that we already know this stuff. Like we know SN2 like the back of our hands. I hope, right? And so strong nucleophile is going to do SN2 backside attack. Primary is best, and there you have it, right? So your alkyl halide is going to go to an alkane. Silly, right? And then for epoxides, it attacks the least substituted carbon when they're unsymmetrical. If they're not unsymmetrical and they are symmetrical, then it can go to either one, and it doesn't matter. But you're going to have to identify those products in the end. Okay. And I don't know, man. That's a wrap. Have fun with it as always. Let me know if you have any questions. Bye.